Hello students, in lecture 4 of advanced calculus, here we shall discuss the continuity of a function of two variables. Certain examples related to this and the exercise is there. First, the continuity of a function of two variables. What is meaning of this? Suppose you have a function f of two variables, then f is said to be continuous at a point f is said to be continuous at a point AB if to every arbitrarily small positive number epsilon there corresponds a positive number delta such that the value of f of xy minus f of AB mod is less than epsilon whenever x minus a mod less than equal to delta and y minus b mod less than equal to delta. Symbolically, the situation can also be written like this: the limit of function f of xy as xy tends to AB is equal to f of AB. Let us visualize the situation. What is the meaning of all these mathematical interpretations here? You see, we know that a function of two variables represents a surface in three dimensions. Here this is origin. I'm representing this f of AB like this. This is the surface here, suppose. This is surface and this is z equal to f of xy. Now you want to check the continuity of this function. Function is this surface at the point AB. The point AB is in xy plane, suppose here. Let I take parallel to this x-axis. I am extending here. Let the distance is delta. The distance is delta. And from on this side, again let this distance is delta. So this part becomes a plus delta and this point become a minus delta. Exactly in the same manner, parallel to y-axis, I can say that this is b minus delta, and in this side let this is b plus delta. B plus delta is here. Fine. So now it becomes a square neighborhood. It becomes a square neighborhood about the point AB. Square neighborhood. So in this square neighborhood means this is the delta neighborhood. The whole situation given here, the meaning of these inequalities is this square neighborhood. And you want to check the continuity of this function f of xy at this point AB. What is meaning of this? Okay, suppose you are extending this upward and you corresponding to this you get certain point here. Then what will be, in fact this is x coordinate, y coordinate, and when you put the value of xy in the function you will get the z coordinate. You will get the z coordinate. And you can also represent it as f of AB, means this is value of f of AB in this case. So how to look at this point here? Sorry, here f of AB is the point here. You can say this is f of AB. And if you take the epsilon distance here and epsilon distance is downward, then this is f of AB plus epsilon, and here it will be f of AB minus epsilon, the point here. So you can see if the situation is like that, this f of AB, this f of AB is close to this point. This f of AB is in around this point, if I'm taking here some point, arbitrary point xy here in the whole square here, I can take anywhere. So that means this x is lying between a plus delta to a minus delta to a plus delta, and y is lying between b minus delta to b plus delta. And corresponding to this f of xy, you will be having some point here, f of xy. If point is here, then you will be having point here. So accordingly, this f of xy lies in the interval f of ab plus epsilon to f of ab minus epsilon. Then you can say that this function is continuous, or you can say this surface is continuous. That means at what point? At point AB. Surface is continuous, or this function f of xy is continuous at point AB. That means at this point there is no hole. Also, because you are talking about the neighborhood here, so at this point as well as around the small neighborhood, around this point, there is no hole in the surface. That is why the surface is said to be continuous at this point AB, or the function of two variables f of xy is said to be continuous at the point AB. Now, if function is not continuous at a point, then it is said to be discontinuous at that point. Now, one important remark here. The meaning of this remark that a point to be particularly noticed is that if a function of more than one variable is continuous at a point, it is continuous at that point when considered as a function of single variable. So meaning of this, you can understand like this, that f of xy is the function and it is continuous at some point AB. Somehow you fix this x as a, that you are fixing the value of x, and y is variable. Now I can consider that it is function of y itself. Now if fxy is continuous at AB, then you can say this hy is continuous at y equal to b. Exactly, if I consider here x as variable and I'm fixing the value of y here. Now you can write it as a function of x only, and then it will be continuous at x equal to a. So this is the meaning of this remark here. So if fxy is continuous at point AB, then if we consider it as a function of single variable, it will be continuous in both the situations. But converse need not be true. If this is happening and this is happening, then it is not necessary that they will lead to this situation. It is not necessary. So now there are more visualizations here, and these visualizations have been taken from this site, Wolfram Math World. You can also see more such visualization at this site. So here we have considered two functions. One is f of xy like this, and another is g of xy like this. So for this function f of xy, the graph is like this, and here the visualization of this function is like this. Now you can see in this situation, if you find the value of f of 0, 0, then you can see 1 upon 0, 0, it is infinity. And similarly in this case, g of 0, 0 is infinity. When g of 0, 0 is infinity, and you try to find the limit of xy tends to 0, 0, g of xy, whatever limit it will come, and if g of 0, 0 is infinity, then you will say that the function is not continuous at 0, 0. That means if we are saying that not continuous at 0, 0, that means there is some hole at 0, and there will be small neighborhood also at which you will having the hole. So this is the situation here. If x is 0, and y is 0 here. When you move these two in the base of this, you will have 0.00 here somewhere downward. So you will be having the hole here corresponding to this point. That is why this function of two variables is not continuous at 0, 0. Exactly the same case is here with this one. Now for this, corresponding to this remark, we can see this example 1. Here you can see, if we have the function f of xy is equal to 2xy divided by x square plus y square, when xy is non-zero, xy not equal to 0, 0, and the value of function is 0 when xy equal to 0. That means f of 0, 0 is simply 0. The meaning of the second part is this one. And meaning of first part, whenever xy tends to 0, 0, the value will be considered like this. Now here, as I explained in the remark, first I focus on this part here. In place of AB, in fact, here we are taking 0, 0. So what we have done here, we have considered y as constant. We have fixed the value of y in the function. When we are fixing value of y, then we have f of xy and limit x tend to 0. What does it gives you? You can see here, if we are fixing y equal to 0, 0 here, 0 here, ultimately all the things are 0. So we are getting 0. And incidentally, the value of f of 0, 0 is also given to be 0. So this thing is 0. Similarly, for the second case, limit y tend to 0, f of 0 y. When you are fixing x equal to 0 and keeping y as variable, now it becomes a function of single variable y. And you substitute the limit y tend to 0 here according to this expression. You will see that the value again comes out to be 0. And of course, this is equal to f of 0, 0. So what is happening here? Here, the limit of this function exists if you are considering it as a function of single variable and you are fixing the other variable. Now you see that limit of this function, that is the simultaneous limit, as you already know from the earlier lectures, simultaneous limit. This does not exist. Why this does not exist? In fact, when you are putting y equal to 0, that means you are approaching 0, 0 along x-axis. And when you are putting x equal to 0, that means you are approaching the origin along y-axis. So along x-axis and along y-axis, you are getting 0. Now let us approach this path. You are approaching this 0, 0 along the path y equal to x. Then you can see f of xy becomes 2x square divided by x square plus x square. That gives you 1. So f of xy equal to 1. And if you put limit xy tends to 0, 0, so this is equal to 1 in fact. So here the value comes out to be 1. And you can see limit in this situation xy tends to 0, 0, f of xy equal to 1, and this is not equal to f of 0, 0. Why? Because the value of this is given to be 0, even in the statement. So you can say function is not continuous. So you can say this f of xy is not continuous at the point 0, 0. Very simple case here. Now, second example, investigate the continuity of this function f of xy at 0, 0 again. So how to solve this? You can see f of xy equal to this thing x square minus y square divided by x square plus y square. The value when xy not equal to 0, 0, and this value is 0 when xy equal to 0, 0. So again in this situation you can see the value of f of 0, 0 is given to be 0. Now you will see that limit of this does not exist. For example, as in the earlier case, when you approach the origin along x-axis, when you approach along the x-axis, what happens? Y equal to 0. When you put y equal to 0 here, the value of this function comes out to be x square divided by x square, and that is equal to 1. So you can say, therefore, you can say the limit xy tends to 0, 0, f of xy is equal to when it is approached along x-axis. Similarly, when you approach it along y-axis, in that situation you will take x equal to 0. But when you take x equal to 0 in this expression, x0 here, x0 here, you will get minus y square divided by y square. So in that situation, what do you get? Xy tends to 0, 0, f of xy, in fact, it becomes minus y square over y square cancelled out, and it is minus 1. So here along x-axis and along y-axis, the limits are not equal. So you can say the limit of this does not exist. Limit of this does not exist. And if limit does not exist at a point, then function will not be continuous at that point. Function will not be continuous at that point. Now come to this example 3. Investigate for the continuity at point 1, 2. It is very simple case. This is the polynomial type of function, and the value of f of xy is this when xy is not equal to 1, 2, and if xy equal to 1, 2, the value is 0. That means the second case means value of f of 1, 2 is given to be 0. Fine. Now let us find the limit xy tend to 1 to f of xy. F of xy is there. You put x equal to 1 here and y equal to 2 here, we'll get 5. So limit of this comes out to be 5, but this limit is not equal to f of 1 by 2 because the value of f of 1 by 2 is given in the statement this is equal to 0. So limit of xy tending to 1 to f of xy is not equal to f of 1 to, therefore the function is not continuous at 1 2. Here 1 2 is a point of discontinuity. But now this function is of a special type. If in place of 0, here we substitute 5, we redefine this function. If we redefine this function and in place of 0 we write 5, then what will happen? Then limit of this is equal to 5 and f of 1 2 is also 5. In that case function becomes continuous. That means you are able to remove the discontinuity involved in this function by redefining this. So such a discontinuity which can be removed by redefining a function is called the removable discontinuity. Example 4. Show that the function f of xy divided by x square y square under root when xy is not equal to 0, 0, and this is equal to 0 when xy equal to 0, 0 is continuous at origin. This function is continuous at origin. So if you proceed as usual, when you approach the origin along x-axis, then you will put here y equal to 0, so value will comes out to be 0. When you approach along x-axis, y-axis, then value is again 0, and f of 0, 0, this means f of 0, 0 is 0. So it will look like that it is a continuous function, but if we take y equal to x square, x equal to y square, etc., etc., and every time you are getting 0, but we have to prove the continuity in general because we cannot find, because many paths as I told you in our earlier lecture, that you can approach this origin through infinite number of paths like this, like this. So you cannot check all those. You can check only some standard ones. So standard ones, you see that if you approach it along x-axis, along y-axis, along the parabola y equal to x square, along the parabola x equal to y square, etc., then the value comes out to be 0, and the function is looking like that it is a continuous function. But how to prove the continuity in general according to our epsilon delta definition? So here we are considering the methodology by converting the Cartesian variable to the polar variables into the polar coordinates. You see, uh, suppose the limit, the value of the function here is given to be 0, 0. Now let's look back to our definition of continuity. What should happen? That value of f of this mod must be some less than epsilon for some arbitrary small real number whenever this x minus 0 less than delta and y minus 0 less than delta. If this kind of situation happens in general, then you can immediately say that the function is continuous. No need to check all these paths as shown here. No need to check. Once you establish this in general, then you don't require to check all these curves here. Fine. So what is meaning of this f of xy minus f of 0? We proceed like this: f of xy minus f of 0, 0 mod. You know f of xy is this, and when x and xy equal to 0, 0, the value is 0. So you can write here, you substitute this value here from here, and f of 0, 0 is 0. You write it like this. Now you substitute the polar coordinate x equal to r cos theta, y equal to r sin theta. You can see r cos theta, r sin theta. In numerator it becomes r square sin theta cos theta, and in denominator this is x square plus y square. So r square cos square theta plus r square sin square theta. You can take r square outside, and cos square sin square equal to 1. So r is in denominator and r square in numerator. So r goes with r. So here we are left with r, and this is for this cos theta sin theta modulus. You know, cos theta, value of cos theta mod is always less than equal to 1. Sin theta is also less than equal to 1. So we can simply write that this whole quantity is less than equal to r. And what is r? If you square and add these two, then r equal to under root x square plus y square. If we assume that this value is less than epsilon, if this value is less than epsilon, when this value can be less than epsilon, this can be less than epsilon if we suppose x square is less than epsilon square by 2 and y square is also less than epsilon square by 2, because here in place of x square, if you write here epsilon square by 2 and plus epsilon square by 2, so that will become 2 epsilon square by 2, 2 goes with 2, and square root is there, so that is equal to epsilon. So that is why we are saying that the whole thing can be less than epsilon if we assume, or whenever x square less than epsilon square by 2 and y square is also epsilon square by 2. So when x square is less than this, then you can immediately say that mod of x is less than epsilon by under root 2. Mod of y is less than epsilon by under root 2. So here I can say that this thing is equal to delta if I am calling it as delta. Because in the definition itself, it is given that delta depends on epsilon. It means the value of delta must comes out to be in the form of, in terms of epsilon. Means delta should be equal to some expression in terms of epsilon. Then we say that delta depends on epsilon. So here we are calling epsilon by under root 2 is equal to delta. Fine. So you can see what we have obtained. F of xy minus f of 0, we have started from this point, and ultimately the thing is less than epsilon, and whenever this mod of x is less than delta, mod of y is less than delta. So you can say this xy divided by x square plus y square under root minus 0 less than epsilon whenever this. So you can say, and this I am saying that it is delta. I am saying that it is delta for your convenience, for making an analogy with the definition. So you can say the definition is satisfied. So you can say the this limit xy tend to 0 0 xy divided by x square plus y square under root is equal to 0. That is, limit xy tends to 0 0 0 0 f of xy is equal to f of 0 0. So this satisfies the definition of continuity. So you can say the function f is continuous at the point 0 0. So here is one exercise where in the first one you can see the following. You have to prove that the following functions are discontinuous at origin. So you can prove the discontinuity, and in this case functions are continuous at origin, and here show the functions are discontinuous at origin again. And here we can show in, you see that this is question number 4. Question number 4, show that this function f has a removable discontinuity at 0.23. F of xy is equal to 3xy. 3xy when xy is not equal to 23 and the value is 6. Value is 6. F of xy equal to 6 when xy equal to 23. Then suitably redefine the function to make it continuous. So that is it about this lecture. The content has been taken from the book S. C. Malik, Principles of Mathematical Analysis. Thank you.